Right, so we've just been talking about self-dualities, which are symmetries of a particular compactification of string theory, which give rise to the U-duality groups. But there are also dualities where the strongly coupled structure of one theory is given by this weakly coupled structure of another, or the duality which is relating one theory to another theory. So a first case I want to consider is two theories, one of which is 2A compactified on a circle down to 9 dimensions, and the other is the 2B theory compactified on a circle of radius where this one has got radius r, and this is a circle of radius r tilde. Now, in both cases, the reduction gives the same d equals 9 supergravity theory with the same low energy effective action. And if you look at the BPS states, there are two sets of BPS states, it turns out that in the analysis of 9-dimensional supersymmetry, there are two kinds of BPS multiplet with slightly different chirality conditions, which I don't want to go into in detail here. But the first one arises as the KK modes for the 2A theory on the circle, or the winding modes for the 2B. And secondly, the other one arises in the opposite way, so the KK modes for the 2B and the winding modes for the 2A. And as we've seen before, we expect there to be a T-duality which relates the theory on a circle of radius r to the theory on a circle of radius 1 over r. The T-duality will interchange momentum and winding modes, and so this leads to the conclusion that these two must be T-dual, with r tilde equals 1 over r in units where I've set the string tension to 1. So this means that the two apparently different string theories, one on a circle of radius r and the other on a circle of radius 1 over r, gives the same theory. So for when r is large, the Kaluza-Klein modes are light. The 2A theory are light, and those BPS states of the 9-dimensional theory are naturally interpreted as momentum modes for the 2A theory. But as r becomes smaller, they become heavier, and then they're naturally interpreted as winding modes for the 2B string. So in this way, we see a duality between these two strings, and we see that two apparently different perturbative string theories, when they're put on a circle, give the same theory. And in fact, there's a similar story for the two different heterotic strings. If you put each of them on a circle, then you get the same 9-dimensional theory, and so they're part of the same moduli space and essentially part of the same theory. There's another related story which comes when we look at the SO32, the theories of SO32 gauge group. One is the heterotic string and the other is the type 1 string. but each of them naturally, their perturbation theory gives rise to different actions, or apparently different actions, but the supergravity theory with that gauge group, supergravity plus super Yang-Mills effective action, is unique. So the two must be related by a field redefinition. And so they must be equivalent theories, so they must be related by a field redefinition. And in fact, the field redefinition includes a relationship between the dilaton of the heterotic theory and the dilaton of the type 1 theory, in which they're related. So that means that the coupling constant of the heterotic theory is 1 over the coupling constant of the type 1 theory, because the coupling constant is given by the expectation value of each of the minus 2 times the dilaton. And so we get that there's a strong, weak duality between these two theories. And another story is that if we look at the 2A theory compactified on a certain four-dimensional manifold known as K3, which is a compact manifold which has certain properties. One way of saying what it is that it's a four-dimensional manifold whose curvature is self-dual, and it's compact, and it's the only one such manifold other than the torus which works that way. And if we look at this and the heterotic string compactified on T4, they both give same effective supergravity theory, which has got a symmetry O420 cross R plus, and in a very non-trivial check, you can see that one can match the BPS states for the two theories, and the relationship between them is another weak, strong duality. The dilaton of the 2A string is minus the dilaton of the heterotic string. When you look at the effective actions which relate from all these, the details of this and the arguments on the previous couple of slides can all be found in the paper by Witten, and it's well worth reading through that, this classic paper to look at the details of these arguments. And here we see that, again, there's a picture that two very different string theories are giving rise, when compactified, give rise to the same effective supergravity theory, and this leads to the conjecture that they're in fact non-perturbatively dual. They're very different as perturbative theories, but the full theory is rather remarkably non-perturbatively equivalent. And as a final example, and in some ways the most important and most dramatic one, is if we look at the 2A string in 10 dimensions. So here we've seen that there are D0 branes coupling to the Ramond-Ramond vector field Cm, and their mass is given by the BPS formula, and it's given by an integer divided by the string coupling constant, so n is an integer, up to some factors of 2 pi and so on, which throughout this lecture I've been ignoring. So we have n equals So mass equals. So we have the mass, which is naught. Well, so naught doesn't really count. So if mass 1 over g, 2 over g, 3 over g, and so on. And note this is very similar to a Kaluza-Klein spectrum for a circle of radius r, which is g. So in the limit, as g tends to infinity, we get an infinite tower of massive modes becoming massless. And we saw that this is exactly what we would expect in a decompactification limit. And this led Witten to the remarkable suggestion that the 2A string is really an 11-dimensional theory compactified on S1, where the radius of the S1 is just given by the string coupling constant. So that the limit, the strong coupling limit, is then a decompactification limit to 11 dimensions. And this is a very remarkable conjecture, but it's led to a lot of it's passed a lot of tests. And so the suggestion, this 11-dimensional theory, this mysterious 11-dimensional theory, is one which is we don't know much about directly, but it's been given the name M theory, maybe M for mysterious. The one thing we do know about it is its low energy effective action, which is given by 11-dimensional supergravity. And this is a theory whose bosonic sector consists of a metric and a third rank antisymmetric tensor gauge field. Let's call it A, M, N, P. And this third rank field will couple to membranes, which are known as M2 branes, and their magnetic duals, which are M5 branes. And when you dimension reduce on a circle, the AMNP, let's do that on the next slide. So we have the metric GMN gives rise to a metric, a vector field G mu y, where y is the direction of the circle, which is identified with the vector, with the Ramond-Ramond vector field C mu, and a scalar GYY, which are identified with the dilaton, and AMNP gives rise to a third rank antisymmetric tensor field, which is identified with the Ramond-Ramond 3 form A mu nu y, which is identified with B mu nu, and that's all, because you can't have two y's, it would give something non-zero. So in this way, we see that we recover all of the spectrum of the bosonic spectrum of the 2A theory. The same word goes for the fermionic spectrum, and moreover, that wrapping the branes of the M2 theory will give rise to the branes of the M theory will give rise to the branes of the 2A theory. So here we see that in particular, we see that the strong coupling limit, the dual theory giving the strong coupling limit of the 2A theory, is rather remarkably given by M theory, an 11-dimensional theory, whose low energy effective action is 11-dimensional supergravity. But it can't just be 11-dimensional supergravity, because it's whatever it is, it's got to give something which, when you reduce down to 10 dimensions, has got to give all the richness of the 10-dimensional string theory. And in particular, you've got to be able to recover all the massive string modes in principle from that story. So to conclude, we've started off with 5 different string theories. The 2A, the 2B, the heterotic, the 2 heterotic theories, and the type 1 theory. And what we've seen is that there are links between all of them. We've seen that there's a T-duality relating the 2A with the 2B theory. There's in other words, putting the 2A on a circle, and that gives the same theory as the 2B on a circle. Similarly, putting the 2 heterotic string theories on a circle, they give rise to the same theory, so that once there's a circle, there's no distinction between those theories. We've seen there's a strong weak coupling duality between the, well, I mentioned briefly, there's a strong weak coupling duality between the type 1 and the SO32 heterotic theory, which means that if you take the type 1 theory, which is this theory of open strings and closed strings, and look at its strong coupling limit, it turns out the strong coupling limit is could be described as a perturbation theory in 1 over the in the inverse coupling of the type 1 theory. And this perturbative theory is in itself a string theory, but it's a very different string theory from the one that we started with. It's given by the heterotic string theory, and conversely. I didn't have time to talk about this, but the strong coupling limit of the 2B theory is again a 2B theory, but the 2B theory, but they're related by an S part of the SL2Z symmetry, U-duality symmetry, which arises here. But whereas in the 4 dimensions, the SL2 interchanged the electric and magnetic charges, in the case of the 2B theory, it interchanges the charges carried by the fundamental strings, or the Nova-Schwarz strings, and those carried by the D strings, and it interchanges those in that way. And moreover, we've seen that this, I've also mentioned briefly, there's a strong weak coupling duality here between 2A on K3 and the heterotic string compactified on T4. So the 2A on K3 is the same as the 2B, as the heterotic string on T4. So this is quite dramatic. These are very different looking string theories, and the fact that they turn out to be non-perturbatively the same is very strange and striking. In particular, our prejudices and intuition based on the low energy effective field theory gives a lot of importance to the space-time manifold in which you're acting. But here we're seeing that the same string theory would interpret the geometry in 2 different ways. in the 2A picture, you'd interpret the internal geometry as being K3, and in the heterotic picture, you'd interpret the internal geometry as being T4. And there's a sense in which both are right, just as in general relativity, when you're looking at the physics, if you look in two different coordinate systems, you describe the same physics. Here, there's in this generalized sense, because you've got the diffeomorphisms enlarged to or enhanced to these extra stringy symmetries. These extra stringy symmetries go beyond those of general relativity, and in this context, it means that the K3, what looks like K3 in when the theory is viewed as a 2A theory, is seen as a T4, a 4 torus, when we look from the point of view of the heterotic analysis of the same theory. And moreover, there's a strong coupling limit of the 2A theory, which gives rise to M theory, an 11-dimensional limit where which is M theory, and M theory on a circle of radius r is equivalent to the 2A string theory as at coupling constant g. So when the radius is small, it looks like a weakly coupled string theory in 10 dimensions, but as you increase the 2A coupling constant, or that corresponds to increasing the radius of the M theory circle, and it looks more and more like an 11th dimension. So if you start off with the 2A, the perturbative theory, which is the 2A given by the 2A superstring perturbation theory, and extrapolate that to strong coupling, what you find is that as the coupling gets larger, the theory no longer looks like a 10-dimensional theory, but becomes like an 11-dimensional theory. And one finds that 11 dimensions emerge in the strong coupling limit. And one finds real evidence for that, for example, there's really 11-dimensional Lorentz symmetry emerging, and it really is an 11-dimensional theory. But in this way, we're seeing that we found direct arrows joining up all of the different string theories. So following these arrows, we can take any of the 5 different string theories and then link it to the others. So that means that whereas as perturbative theories, there are 5 distinct theories, these are all essentially seen as different parts of the same theory. They're all linked together, so there's this big theory which contains all of them. And M theory is seen as the theory which gives rise to all of these different theories. And in fact, starting from the 11-dimensional M theory, there are constructions which give rise to each of these different theories, albeit going via putting the theory on a torus or on K3 and going through a chain of interactions. So in this way, we see that instead of there being that we're seeing all of the different string theories unified in one theory. So the question about why are there 5 different quantum gravity theories have a dramatic answer, in fact, saying no, there are not. When you look at these non-perturbatively, they're all different facets of the same theory. And when I was giving a lecture on this soon after the Witten's paper in 1995, I found a nice diagram which I thought suggested a nice picture encompassing all of this structure. So we have some picture of the moduli space HE. So we're thinking of a moduli space, and then going off in different limits will give rise to different aspects of the theory. So perhaps I'll have one more cusp giving the 11-dimensional theory. And so these could be thought of as all different. Each of these different perturbative theories could be thought of as different corners, different limits of this underlying theory, which we still have very little control or understanding of, but it's been given the name M theory. And we can think of we understand it in different corners of the moduli space, where one of the particular moduli is such that it becomes a small coupling constant. In one corner, the theory could be analysed as a perturbative 2A string, in another as a perturbative 2B string. In another, it's a theory whose low energy limit is 11-dimensional supergravity, and so on. And so we have this rather satisfying picture where we have all of these different, apparently different string theories arising as different corners of one underlying theory. Rather strangely, very little has been understood yet directly about M theory. There's a lot been understood about its particular limits, in particular about the 11-dimensional limit and the different string theory limits. And I think, but we don't really understand, for example, what its fundamental degrees of freedom are. We have a picture that really, it doesn't seem to have a natural coupling constant, so it doesn't really have a perturbative definition. Perturbative definitions arise, for example, when we put it on a circle and expand in the and use the radius of the circle as a coupling constant, and then the resulting theory is understood as a 2A string theory, because the radius of the circle is interpreted as a coupling constant of the 2A string theory. So it's a rather rich and remarkable picture. I haven't been able to do justice to the full intricacy of it, but in the list of references I give a lot of further reading, and I think hopefully what I've talked about today will provide an introduction to what is really a vast body of material, and I hope that this will be a guide leading you to further reading. Okay, so thank you very much for your attention.